morning to all. Today we'll be discussing about the fifth part of the thin cylinders. I mean tutorial 5 of thin cylinders. So before going into the lecture, once we'll revise the last class. So what all we have learnt in last class. In the previous class we have learnt derivation of volumetric strain. We have derived the equation for volumetric strain, and also we have solved some numericals based on volumetric strain and change in volume, which are of important in this topic for your examination point of view. So in this class you will be able to know how to calculate the thickness of the cylindrical shell based upon the various values like internal pressure, hoop stress, longitudinal stress, and other things. So ultimately it is like we are designing a cylindrical shell with respect to the conditions which it will be subjected in the future. As every theoretical part is completed in the previous 4 tutorials, now we'll apply those theory part or concepts in certain numericals in this class. So even though we have solved certain numericals in the previous classes itself, further we'll discuss some more new problems based upon these concepts. So if we go into the numerical, a cylindrical compressed air drum 1.8 meter in diameter has to sustain, so diameter is 1.8 meter, has to sustain air pressure of 2 Newton per mm square. If the safe stress in the material is 70 Newton per mm square, find the necessary thickness of cylinder wall. So we have to calculate thickness of the cylinder. What he has given here, he has mentioned safe stress in the material. So safe stress means we have two different stresses here. One is hoop stress and another one is longitudinal stress. So in these two, which is safe stress? That we need to identify, or else you won't be able to solve this simple problem, as it is seeming to be a simple numerical. Until and unless you find out this logic, you won't be able to solve this numerical. So here, if you go into the solution, diameter is 1.8 meter, air pressure is 2 Newton per mm square. Safe stress, we need to consider hoop stress. Why we need to consider hoop stress here? That we need to know. So I have already mentioned in various tutorials that sigma h is equals to 2 times of sigma L. It means sigma h is greater than sigma L, right? That means if a cylinder is safe for longitudinal stress, it doesn't mean that it will be safe for Hooke stress, because sigma L value is lesser than sigma h. Or else in the contrary, if a cylinder is safe in Hooke stress, as it is having a more value than longitudinal stress, it will be ultimately safe for longitudinal stress as well. So this logic you need to understand, then only you will be able to solve this numerical. So because of that condition only, we are considering what he has given safe stress as Hooke stress. So thickness T we need to find. Hooke stress is less than or equals to allowable stress, safe stress. Yes, because if Hooke stress is greater than allowable safe stress, the cylinder will get damaged. I mean to say, the cylinder will fail. So Hooke stress should be less than or equals to allowable safe stress. I think you got this logic. If the cylinder is safe in Hooke stress, it will be automatically safe in longitudinal stress as well. But the reverse is not possible because Hooke stress is having more value compared to longitudinal stress. Now, if we substitute the Hooke stress value PD by 2T, we have P value, D value, and FH value, that is nothing but 70, and here we need to calculate T. So 2 into 1800 by 2 by into 70 gives us 25.75 mm. So this thickness we got if we equate Hooke stress to allowable safe stress. We are equating it. That means at this particular thickness, the cylinder is just safe to this particular pressure. It is just safe. Okay, it means it is the limit, lower limit. So if we provide thickness which is greater than 25, greater than 25 mm, 0.75 mm, the cylinder will be safe for any stresses or any pressures. So ultimately, therefore, the thickness of the cylinder wall should be greater than or equals to 25.75 mm. That is what he has asked us to find out. So find the necessary thickness. He has mentioned the necessary. So necessary will be 25.7. If you take more than this value as thickness, that is much more safer. So on the better conditions, if you take the 26 or 27, that will be much safe for us. So even though this numerical looks like a simple problem, there is a bit logic involved in it. In the same way, if we look at the next numerical, a vertical thin-walled standpipe is 4800 mm in diameter. So small d is 4800 and stand 30-meter height. The allowable working stresses in the tension is 100 Newton per mm square. So length is 30 meter and allowable working stresses in the tension is, okay. So what is the required wall thickness? Assume the pipe is filled with water and internal pressure he has given as W into H. This kind of equation we have seen in one of the previous numericals also. So here he has given allowable working stress. Again a same kind of terminology, similar kind of terminology like in the previous problem, like safe stress. So here what he has mentioned, he has mentioned allowable working stress, or it can be written as allowable safe stress. So again, sigma H or sigma L, which one is 100 here? It should be sigma H. So sigma H equals to 100 Newton per square. So D is 4800. P double into H, W is given 9.81 into H is 30. We got 294.3 kilonewton per meter square. So if we substitute this into Newton per mm square, we'll get this value. Now allowable working stresses, maximum stress Fh equals to 100. This can also be written as allowable working stress. So Fh is equals to Pd by 2T, and from here it is similar to the previous problem. Small t we need to calculate. We got 7.063 mm as thickness. So the thickness of the pipe required is, it should be more than this value, because this decimal value is very difficult to maintain in practical. So it is better to increase the thickness to the next round figure. It should be next round figure on the higher side, not on the lower side. If we place the 7 mm thickness, that won't be sufficient for taking such stresses. So to be on the safer side, we need to increase this value and we need to consider as 8 mm. This is for our safety. Okay, we should not round it out to 7, because as 7 is nearer to this value, we should not round it off to 7, because 0.063 mm thickness we are removing it. So if we remove the thickness of the cylinder, it will affect the total working condition of the cylinder. I mean to say, it may not handle the internal pressure, right? So it is better to round it off to the next higher figure. So that should be 8 mm, or in case if you can provide 7.5 mm also, it is permissible, but not 7. So in this numerical, you need to understand which value we should take as 100. So these are all just terminology differences. Safe stress, allowable working stress, all are of same conditions which we need to observe them. So with this knowledge, we'll solve one more numerical. A water main of 1 meter diameter contains water at a pressure head of 80 meter. If the specific weight of water 9.81 kilonewton per meter cube, find the thickness of the metal required for the water main. So thickness of the metal. Given that maximum permissible stress in the metal is, again we are seeing the different terminology. In the first numerical we have seen safe stress. In the second numerical we have seen maximum allowable stress. In this a bit different terminology, which is maximum permissible stress. So diameter of the pipe is 100 mm, 1000 mm. Specific weight W into H we get internal pressure. So 0.7848 Newton per mm square is the pressure. So here he has given maximum permissible stress. No need to get confused. It is similar to the allowable stress or allowable working stress. Both are same. So maximum permissible stress is equals to allowable working stress, right? So these two terms are similar. So maximum will be sigma h, as I already mentioned. It will not be sigma L. So we should not use PD by 40. We should use PD by 20. So hoop stress sigma h is equals to PD by 2T, and P we have 0.7848 dig 1000 by 2 into 20. We get 19.62 mm. So that is what we need to find out here. Find the thickness of the metal required for the water main. So till now we have seen three different numericals of finding thickness of the pipe or thickness of the cylinder or thickness of the vessels based upon the various stresses like safe stress, allowable stress, I mean to say allowable working stress and maximum permissible stress, and which are subjected to various internal pressures. So this is how we need to fix the thickness of the cylinder for which they are intended to use. So the thickness of the pipe is found by making the maximum stress induced in the pipe material equal to maximum permissible stress in the pipe material. So here you need to note this point. The thickness of pipe is found by making the maximum stress induced in the pipe material, right? We are equating the maximum stress induced in the pipe material equal to permissible stress in the pipe material. So this is maximum stress induced in the pipe material, and that will be equals to maximum permissible stress in the metal, right? So that means we are comparing the pipe material to the pressure which is applying on it, right? So whatever the stresses which are developing in the material, we are equating it to the stresses which are coming onto it. So then only we can know, we will be knowing the equilibrium condition, right? So that is why we are using such relation. So hence the thickness of the pipe should not be less than 19.62 mm. So this condition is important. If you clearly read this, you'll understand why we are equating pipe material stress or stress in the metal equals to certain allowable stress in the pipe. If you go into the next numerical, calculate the minimum thickness of wall required. So small t for a thin cylinder of 1 meter diameter if it is to withstand an internal pressure of 3. So P equals to 3 Newton per mm square. Longitudinal stress is not to exceed 25, not to exceed or less than or equals to. Group stress is not exceeding 35 Newton per mm square. So considering the longitudinal stress, he has given two conditions here. He means to say find the minimum thickness by considering these two conditions, right? First condition is if longitudinal stress is less than or equals to 25 mm, 25 Newton per mm square. And second condition is hoop stress less than or equals to 35 Newton per mm square. So by using these two conditions, we'll get T1 and T2, right? So by comparing these two values, T1 and T2, he is asking us to find minimum thickness of the wall. So by considering first part, by considering the longitudinal stress, we get Fl equals to PD by 40 and T as 3 into 1000 by 4 into 25, we get 30 mm. Means this is, let us say, T1. So by using the second condition, that is considering the hoop stress PD by 2T, 3 into 1000 by 2 into 35, we got 40 mm. So here you need to observe these things nicely. As he has asked us to calculate the minimum thickness, it doesn't mean the value which is minimum in T1 and T2 is the answer. Here we got T1 as 30 and T2 as 40, right? So it doesn't mean minimum means in these two, minimum is 30, 30 is the answer. That is wrong. The same concept applies here, which is that sigma h is greater than sigma L. If the cylinder is safe in hoop stress, it will be automatically safe for longitudinal stress. So here we got thickness in, while considering hoop stress, we got 40. While considering longitudinal stress, we got 30 mm. So clearly 40 mm is greater than 30 mm, right? But even though 40 mm is greater than 30 mm, I mean to say the thickness is more than compared to the longitudinal stress, we need to place this thickness only. Because if we place this thickness only, it will be safe for hoop stress. Automatically it will be safe for longitudinal stress. So just consider if we place 30 mm as our thickness. So if we place 30 mm as thickness, what will get sigma h value? Same 25, right? Because we got this value by using 25 mm. But what he has mentioned here, hoop stress is not exceeding to 35 Newton per mm square. So if you place 30 mm, it will not carry 35 Newton per mm square stress, and it will fail in hoop stress. It may be safer in longitudinal stress, but it will fail in hoop stress. So that is a disastrous thing. So even though while considering hoop stress we are getting maximum, I mean to say maximum between these two conditions, T more than longitudinal stress condition, we need to place that particular thickness itself as our minimum thickness to be on safer side. I mean to say the cylinder will be safe only when if you consider the Hoover stress condition and calculate the thickness of the cylinder. So that is why, therefore, minimum thickness of wall to be provided is 40 mm. Such type of things and such type of numericals, it will be useful for your competitive examination point of view. So we'll solve both the values, and then options A30 will be there, B40 will be there, C some 50 and D some 25. As we got these two values, in a hurry we'll say we'll select this option because it is the minimum between these two values, 30 and 40. But ultimately A will be wrong and B is correct. Okay, this is a small thing, but it requires a lot of attention. So I hope this concept is also clear now. We need to consider the thickness based upon the stress conditions. That, mean, that means whether you need to consider Hoover stress or longitudinal stress while calculating the thickness. So with this, we can say that we can conclude, I can say that we can conclude this particular chapter, thin cylinders, is been covered completely with this tutorial. We have seen each and every concept, and also we have solved various numericals covering every concept in this topic. So conclusion, with this class we have completed all kind of numericals based on various stresses, strains and change in dimensions of a thin cylinder, and we have solved some volumetric strain numerical also. So I further recommend you to practice some more similar numericals from various textbooks to get familiar with this topic. So if you keep on solving the various numericals, your concepts will be much more clearer. I mean to say, in which condition, what kind of concept we need to use, and how we need to correlate the things. Such type of things will be clearer for you if you solve some more numericals on the particular topic. So if we once revise from first tutorial to this tutorial, in the first tutorial we have studied that how we can define a thin cylinder. If T is less than or equals to less than 20 times of D, it is the basic definition of a thin cylinder. If T is greater than or equals to 20 times of T, it is thick cylinder. And next we discussed about the hoof stresses and circumferential stress, longitudinal stress. So hoof stress PD by 2T, longitudinal stress PD by 4T, and we have seen some one more stress which is known as radial stress, and also we have mentioned in our assumptions that as it is having a negligible value, we are considering sigma r as 0, right? And because of these hoof stresses, we have seen some strains are developing. There is epsilon h, epsilon l, and epsilon v, volumetric strain. And we have each equation for these as well. So by using these equations, we have solved various numericals, which includes various stresses and various strains. And we have one more important relation: change in volume is equals to volume, original volume I mean to say, into epsilon L plus 2 into epsilon H. So this is one more important equation in this topic which you need to remember. So these things we have discussed in the previous tutorials, and we have solved various numericals on each and every concept. And also in this tutorial we have discussed about how to finalize the thickness of the cylinder based upon various conditions. So T is generally depends on stresses and internal pressures. So stresses means sigma H or sigma L based upon the given conditions, and internal pressure is P, that is subject to a certain oil pressure or any water pressure or any different liquid pressure or gaseous pressure. So based on these conditions, we can finalize the thickness of the cylinder, which is a major part of this topic, because again this is related to the initial thing. If this thickness is less than 20 times of diameter of the cylinder, then only we can consider it as thin cylinder, right? So we are started with thickness and we are ending with thickness of the cylinder. So in this way, whatever subject or whatever topic you are studying, you need to relate the things. I mean to say, from where you are starting and where you are ending, and in between, what is the relation between each and every topic. So if you move this way, the concepts will be very much clearer to you, and also you can remember the things for a very long time. As so many people will say, there are many equations in this. They'll say that it is very difficult to remember the equations and everything. So nothing to be worried. You need to just concentrate how the things are going on. I mean to say how they are started and how we have ended in one particular topic. So here we have started with thickness, and ultimately again we are ending with the thickness by finding the value. I mean to say ultimately the thickness refers to the type of cylinder, right? So this is how you need to proceed. So which will be helpful to you in dealing with any subject or any topic. You just need to observe how the things are going on. So with this, I'll complete this session. I conclude with this session. I hope you are clearer with these concepts, and I recommend you to solve some more numericals from various textbooks so that you can easily grasp the concepts, or else you can easily understand the things which you need to do just by reading the question itself. I hope thin cylinders topic is very much clear to you, and in the next session I'll come up with another topic of the theory of structures subject. So have a good day. Thank you all.